If you can see from the transmitter to the receiver, you can get power there. This long distance optical beamed power is a lot closer to reality than a lot of people think.
This is EnergyCast, and I'm Jay Downhauer. Today we're talking about long-range power beaming, delivering big energy across long distances. Way back in episode 32, we discussed the potential of wireless charging. The guest was specializing in near-field technology that would charge things like your electric car while it sits over a specialized pad. There were two ways to do this: inductive coupling, where power is transferred through magnetic fields between coils of wire, and capacitive coupling, using electric fields between two electrodes. In my monologue back then, I also teased how long-range power could be delivered. The choices are still the same: microwaves or lasers. Microwaves are ideal because they don't lose much of their impact across distances. When I worked as a TV producer, I'd regularly dial in live shots from the trucks. The signal was crystal clear as long as the microwave signal from the truck's antenna hit our tower back at the station just right. Lasers are the technology my guest is developing. If you look at a chart of the electromagnetic spectrum, actual lasers fall just to the left of visible light in a zone called near infrared. While there's a slight drop-off in signal thanks to the atmosphere, the area of concentration lasers provide are much smaller, small enough to hit a receiver on a drone, for instance. My guest says they'd likely position their lasers on a tower and then directionally beam that laser energy to a receiver, which would look a lot like a solar cell. This has a lot of exciting potential, especially considering you could beam several kilowatts. You could beam power this way to neighborhoods, islands, hospitals, military bases. We also discussed my guest from episode 50, Paul Jaffe, who has been developing the Solar in Space program. My guest today says increasing power is as simple as adding a cluster of lasers rather than making one laser more powerful. And that's an important issue to overcome in the public's imagination, especially when the first thought of a laser transmitting energy back to the surface is the Death Star.
You may fire when ready.
What?
Commence primary ignition.
My guest says a lot of their technology development has been focused on making sure the lasers are safe. If so much as a pigeon got close to the laser's beam, he says, sensors would shut off the laser temporarily. The same would go if one day a Cessna flew in between a solar array in orbit, beaming power back to Earth. But the idea that you could quickly, effectively, and safely transmit power across miles without the need for any new power lines is one of the many benefits of long-range beaming. My guest today is Tom Nugent, co-founder and chief technology officer at PowerLight Technology, a long-range power beaming company based outside of Seattle. PowerLight got its start as laser motive back in 2005. They have set 3 world records for beaming power over light. The key to their technology is their unique receiver design for collecting energy, as well as their safety systems I mentioned earlier. The company is also focused on a fiber optic power technology, which if I were a betting man, I'd assume would eventually replace traditional copper lines. We'll see if he agrees. I hope you enjoy my conversation with Tom Nugent. We're here with Tom Nugent, CTO and co-founder of PowerLight Technologies. And Tom, the last time I talked about power beaming, it was with Paul Jaffe at the Naval Research Laboratory for my Solar in Space episode. He said that for high power beaming, you need to use microwaves or lasers. Is there another way?
No, those are the main ways. And we've been working with Paul in some of our power beaming work. It really comes down to what are the possible objects that can emit certain wavelengths, what can absorb them and convert them, and then what will the atmosphere absorb? And so you wind up being in this near optical range where we're doing lasers, or sort of the microwave millimeter wave, radio wave area where you have these nice windows in the atmosphere. And so other wavelengths would be possible, but we don't necessarily have the devices to convert in those wavelengths, or the atmosphere is just too opaque in those wavelengths.
Now, for a lot of these technologies, it was critical to have line of sight. I used to work in TV. We used those TV trucks, right? You could get a crystal clear signal from those trucks, but the microwave antenna had to be aimed directly at the TV tower. So do you have to have line of sight to whatever you're beaming power to?
Yeah, you can imagine it's sort of like a flashlight, or people know laser beams. It has to be able to make it from the transmitter to the receiver. Our general rule of thumb is that if you can see from the transmitter to the receiver, either by eye or by telescope, you can get power there. And there are some options for bouncing off an intermediate mirror to, say, get over a mountain or things like that. But it does require that direct line of sight.
Help us understand, what is the difference between those TV trucks we had, which were sending, I think, what we would consider a signal, and what you're doing where you're using essentially those kind of beams to send power?
Yeah, there's a couple of ways to answer that. One way is, well, the power is just a lot more power going through that beam. But for transmitting data, you care about the receiver getting enough of the signal to be able to decode that signal and turn it back into data. And if some of the power that was emitted misses the receiver or gets absorbed along the way, it doesn't matter as long as you can get the data out at the end. And that just talks to how strong your signal is relative to any background noise. For power, we care about getting all of the power there. In general, we try to focus the beam very tightly so that we can capture all of that power at the receiver in order to then convert it back into power and be able to use it.
Is there loss of power over distances using this technique?
There is. For any electromagnetic wave, the atmosphere may absorb or scatter some of it. And in the wavelengths we use, that's relatively minimal. Again, if you can see it, the amount of power that gets lost between you and that receiver can be relatively minimal.
And what kind of distances are we talking?
Right now, we're focused in the kilometer ranges. We've done demonstrations at shorter distances, as short as 50 meters or even 10 meters. But that's one of the things that sets us apart from other groups working on wireless power. For what we're doing, optical beamed power, we can send it kilometers or even tens or hundreds of kilometers or further, but we are focused at this roughly 1 kilometer range, from hundreds of meters up to a few kilometers for the early applications.
And so let's talk about these applications. There's a graphic of a drone and a tower beaming energy to it on the homepage of your website. Is that the space you're looking at mainly at this point?
There are a lot of different possible applications. And one of the challenges we faced as a startup has been trying to sort through all those different applications to pick the right first one to go to. Drones are very interesting because there are some use cases where you don't want to have the drone land because you're taking your communication node out of the air, or you're taking the eyes off of whatever it is you're watching. The problem with drones is you really can't run an extension cord up to them, at least not very easily, and certainly not if they're going to fly very far away. When bringing this new technology to the market, drones are appealing because of that strong need for power. It's not a matter of trying to fight on having a slightly lower expensive way of delivering energy. It's they can't get it there any other way. One of the other areas that we think is even nearer term is for point-to-point on the ground for groups such as telecom, as well as for the military. In both those cases, there are remote sensors or remote communication nodes. And there's this time component where you want to be able to set up, for example, your cell tower repeater as quickly as possible. And in the case of the telecom industry, if you need to wait for the power company to run a power line, you might be waiting months, or I've even heard cases of years, waiting for that power line to be run. By being able to deliver power wirelessly, you can get it set up immediately and start using that communication node or other device while you're waiting however long for the power company to run a power line. And that initial application, this point-to-point on the ground, is the one that we are seeing as the first application that we'll be selling into. One of the things that we really want to communicate to everyone listening is that this long-distance optical beamed power is a lot closer to reality than a lot of people think. We are expecting to have sort of first prototype units out for customers to be field testing and using in roughly a couple of years.
I take it the drone has a battery on board so it could run on its own for a little while if it lost connection to the tower, say it went behind a mountain?
Yeah, exactly. And that's true for any application where we would have some amount of energy storage, usually a battery, at the power receiver, because not only do you need to keep providing the energy locally if, say, the drone goes behind a mountain or something or out of your line of sight, but also because of of the safety system, one of the big advancements we've been doing to make this reality is making it safe. We have sensors that detect if anything is approaching the power beam, and it will temporarily shut that off so that nothing gets exposed to the hazardous levels of light. And then as soon as the beam path is clear, it turns the laser back on. And so whether that's a bird or a tower, if you're following a drone, we will intermittently turn the laser off to be able to keep everything safe, and then it comes back on. And so the battery on the drone or whatever other device you're powering will handle that brief outage of the laser. And this allows you to be able to deliver sort of a smoother average level of power to the receiver and handle any momentary spikes in the demand, say from the propellers of a copter, by having that battery there able to handle those momentary spikes in the power demand.
Sure. Does your tower, whatever is beaming to the drone, does it constantly have to be pointed directly to whatever it's trying to provide power to? Does that make sense?
Yeah, no, we have a gimbaled transmitter that is steering the beam to keep it centered on the receiver. And you could think of that we operate in a sort of pointing accuracy regime that's somewhere in between, say, directed energy weapons that really have to, keep that beam really, really tightly focused on a narrow spot on one end, and radio or optical communications on the other end, where they need to sort of be pointing, but they can have some amount of error. We're sort of in between there of pointing at the receiver and keeping it on there. And the job we have to do, like I said, is much easier than what other types of pointing are done for some other applications. And so because the receiver can always sort of tell you, hey, here I am, it's not much of a technical challenge to keep the beam roughly centered on the receiver.
So if you were providing power for multiple drones, say, off of one tower, you would need multiple gimbals for each drone, right?
Correct. Or you can timeshare. There's a possibility where you send power to one drone. And we've done this in the past where you provide not just the power to fly, but excess power so it can fly and charge its battery. Then once its battery is full, it can go maybe even beyond the line of sight to do something. And now you can have another drone that you are charging and powering within your line of sight, and you can sort of go back and forth between them.
I've worked in transmission. We've talked a lot about microgrids on this podcast. I guess you can't run all the power out to a place, but a limited amount, maybe distribution levels of power. Could you just beam it to a neighborhood?
Yeah, you could. What optical beam power does is take the electric grid and extend it beyond where it can currently reach. And that could be within a city to, like I say, power telecom node, but it can be after a natural disaster where you need to get power into a neighborhood because the roads are torn up and you can't easily drive in new generators and fuel. There's been some people looking at beaming power to islands or other sort of remote places where there's a few houses where it could be difficult to get power some other way.
How much power can we transmit wirelessly? I believe folks think that one day we'll be beaming transmission level energy, hundreds of kilowatts, right? But that might not always be the best idea, right? I think you can ionize the atmosphere with that much energy, right? Unless it's going through wires.
To your very first thing you said, if a majority of the public is even aware of power beaming and think it's going to happen, then we've come a lot further than I had thought. Because we run into people who are technology scouts who in some cases didn't realize that power beaming was real and was this close to reality. But to your point, we have delivered a kilowatt of power over some distance, and the work that we're doing in the next year or so will be for roughly a kilowatt at a kilometer scale. It can scale up to higher power levels. It's easier to add power than it is to add distance by just adding more lasers and more photovoltaic cells. The beam intensities that we're using are much lower than what would ionize the air. Shipping larger amounts of power is not a problem when it comes to increasing the amount of power. Your beam size would effectively get larger as you're adding power to keep that intensity at the right level.
Right. I can't remember if it said kilowatts or kilovolts.
Yeah, no, it's always interesting talking with different users when people talk about voltage or wattage. We think in terms of wattage, how many kilowatts are we delivering? It's effectively a type of solar array. And so depending on how that is converted, you can get whatever voltage you need at that remote end.
Okay. It's weird when you're thinking about power, but I believe it's the FCC regulates what parts of the light spectrum are used for what. Am I right? I mean, about 20 years ago, we were all going from SDT TV to HD. And so all of that traditional TV signal was basically getting cleared out. And I think that most of the TV signal ended up getting eaten up by the cellular companies, right? So what band are you on? And do you have to be careful what kind of light you're transmitting to keep from interfering with TV signals and phone signals and all the other things that are out there?
Yeah, you're right. The FCC regulates, I believe, up to 300 gigahertz. We are 3 orders of magnitude higher frequency than that. We operate in the very near infrared, so just outside the optical range. The FCC doesn't regulate visible light or near infrared. The organization that actually regulates laser products is the FDA. Interestingly enough, there is a group called the Center for Device and Radiological Health that regulates not only lasers, but X-ray machines and things like that. We are so far outside of the frequency range for things like, you say, television or cell towers and everything, that there is no interference at all.
Does light on different frequencies affect other light?
No, not really. Not just from the light waves being nearby. That's one of the nice things about, say, lasers as opposed to microwaves for beamed power is that there is no interference like that. Whereas if you're operating in, say, microwave power beaming or millimeter wave, you may get sidebands or side lobes that are at a very close frequency. Those are generally in the 2.5 to 100 or so gigahertz. And the optical power that we're using is up in the 300 terahertz range. And so it's 300,000 gigahertz. So it's much further away, and there isn't really interference between those.
I wanted to go back to Dr. Jaffe, and I was pleasantly surprised when I saw your video. I was like, yeah, this seems like something Paul Jaffe would do. And then Paul Jaffe's in the video.
Yes.
Which I thought was great. His space solar technology. Could you help make that a reality? I believe the biggest challenge with transmitting solar energy back to Earth from space is that you need a lot of collectors on the ground. At least that was how he explained it. You're also extremely high above the Earth. You're not just in sub-orbit. I mean, you are really far up. You'd have to be very precise. So how would you help make his dreams a reality?
The interest in beaming power from space is one of the things that got me down this path back when I was, in high school and in college many decades ago. It sort of has been an inspiration for what we're doing. The interesting thing when you talk about grid level power transmitted, say, from space, there are advantages that the microwaves have over lasers in terms of being able to lose less power if there are clouds in the way. Ultimately, when you're trying to put a gigawatt of power in space, you will want to go to microwaves. And that dovetails nicely because microwaves, because they're such a longer wavelength, require much larger antennae on the transmit and receive end. You need sort of this kilometer scale antenna and kilometer scale receiver on the ground for that. Lasers are interesting as a sort of a proving ground or clearing the way for power beaming because it can be done at a much smaller antenna size, smaller receiver size, and smaller power scale. So before you go and launch, a million tons of hardware into space to beam power, you're going to want to launch something a little bit smaller. And you'll want to do it for sort of high value applications, things like a remote island or for the military, a remote base where it might be hard to resupply. Doing power beaming from space with lasers can make a lot of sense because you'll be able to prove it out. And there's a lot of aspects of beaming power from space that are independent of whether you're using microwaves or lasers to transmit it. And so you'll prove that out, be able to do it at a smaller, more affordable scale, and be able to have value at these kilowatts, tens or hundreds of kilowatts scale with lasers for these remote applications, whether it's the military or certain remote islands. And because of the pointing accuracy we can achieve, we will also be able to keep those receivers proportionally smaller. Now, one of the nice things is that a laser power receiver is converting light, and even if the laser's not on, sunlight will be able to provide some power to those receivers. One other thing that people worry about when they hear the word laser is a death ray. And one of the big things that we're doing is making it safe and showing that it's safe. We have demonstrations where we have our power beam operating right overhead, and we can put a hand or other targets through it and show that it shuts off and it's safe. That's part of laying the ground to prove that this can be as safe as electric wires that have insulation around them so that you can operate it, delivering this power overhead completely safely with no more concern than you have for any power line, and ultimately be able to then deliver some of that power from space, if it makes sense.
If we do get to that, and I really hope we do, one of the fun things that Paul did one time, I think I asked him, where does the array have to be in order to not get shadowed by the Earth at nighttime? And he's like, well, you can do it this angle and it'll always be facing the sun, wherever it's beaming to. So what about the airspace where the energy would be collected on the Earth? Would that just be a no-fly area?
Yeah, we try and take a multi-layer redundant approach to safety. Our safety sensors, we don't just have one. We have multiple ways of trying to detect if something is flying into a beam. If you're doing that kind of permanent installation at larger power, you might try and have a no-fly zone around it, but you also have to allow for people ignoring those rules or having some accident and getting into it anyway. You would still have these safety systems so that if, like say, if some Cessna started flying in, you could turn off that beam briefly while you chase it out of the airspace or radio them and get them to fly away. And then you can turn that laser right back on to keep delivering the power.
Gotcha. One of the other things it said you offered was energy over fiber. And this is something that I've seen in the past. I'm curious, would we ever get to the point of replacing fiber optics for traditional conductors that we would see in power lines for high voltage?
It'll be a long time before it would replace sort of grid scale power. It is theoretically capable of carrying insane amounts of power. The amount of power that you can put through a fiber that's less than a millimeter wide is measured in tens of kilowatts. But because of economics and the efficiencies, I don't know that it would replace full-scale grid line power. Now, there is a lot of interest in power over fiber when you need voltage isolation. And this is in things like around high power lines. For example, sensors that are used to monitor our high voltage distribution lines, those need to be electrically isolated so that you don't accidentally short your power line down to ground. In those types of situations, power over fiber makes complete sense because that fiber is not conducting. And it also makes sense in smaller scale applications where you're doing research. And there's various high voltage research where you need that voltage isolation. One of the other areas that the power over fiber is being used and that we've demonstrated is for underwater drones, where it's a challenge to run a copper power line, say a kilometer underwater, for an underwater vehicle because it requires so much insulation and wrapping to make it neutrally buoyant that it's just generally not done. It slows down the vehicle too much. Fiber is much thinner, and so you don't have all this insulation around it, and it can deliver power for those underwater vehicles and allow them to be as autonomous as you want them to be.
So you don't have to shield it?
Correct, yeah. It's a dual problem underwater where you have to insulate it to keep the conductive seawater from shorting or galvanizing your electrical connections. And because the copper is so dense, you need sort of a negative density or a buoyant material around it to help it float or be neutrally buoyant. And fiber doesn't have either of those problems.
I guess finally, wanted to ask you about where the company is at this point. This kind of technology, you could go into a lot of sectors, so you kind of have to be choosy at this point who you decide to dance with first, right?
Yeah, and like I said earlier, this technology is closer to reality than a lot of people realize. We have been very lucky to work with Paul Jaffe and the Department of Defense to mature and prove out the technology that we've been developing for years before. And we're now talking with some large corporations who are interested in this for industrial applications. And we're looking to have that first product out for initial testing in the next couple of years. We are growing and looking for others in similar applications who may be interested in partnering and licensing some of the technology to be able to bring it to reality and have these products start being used in industry and the military and eventually growing from there.
Right.
And one of the things I should add to this, we're always looking for more people. So if there are engineers in particular, please reach out because we're always looking to add some bright people to the team as we're growing.
Yeah, great point. Whenever I do panels, and a lot of times these are at colleges, I ask all the panelists who's hiring, but then I say, okay, I hope you brought business cards because I know that's probably the foremost thing on a lot of those kids' minds.
Yeah, exactly.
Tom, I'm going to finish with a lightning round of your thoughts on different energy technologies, starting with natural gas.
It is transitioning us as we are decarbonizing.
Crude oil.
It has, I believe, been even decreasing lately. So again, as we are decarbonizing, it will continue to decrease in usage. And hopefully we can leave enough in the ground so that the other applications where we sometimes need petroleum will still be there.
Nuclear.
Nuclear is the best way for us to decarbonize. We need to keep growing. I was really excited to hear your interview with NewScale recently, and I'm just really excited to see the nuclear growing up and maturing and being deployed, and it's the way we're going to decarbonize.
Coal, and I'll add coal with carbon capture.
Coal has really been decreasing just through natural market forces, and it is part of decarbonizing. And carbon capture is going to be very important because we know that we need to have negative effective emissions. And there's some interesting things out there for carbon capture, and being able to make it economical is going to be the big challenge.
Wind.
Wind is interesting, especially out in the ocean or near the ocean where you can get a lot of wind. There's issues with disposal and, again, transmitting the power from where it's most collected to where it's most needed. But it can help to supplement some of the baseline.
Solar.
Solar also has been great and a huge growth over the last few decades. It also, I think, will start to have a disposal end of life problem, and will sort of hit a saturation point as it becomes a larger fraction of the grid. But it is very helpful, and I think even more so at the sort of house and small scale, as opposed to solar farms where it takes up a lot of land.
Biofuels.
I'm not as familiar, but I think those make sense in the long term, decades out, as we start really decarbonizing. I'm just not as familiar with how efficient they are at growing nowadays.
Hydroelectric.
Out here in the Seattle area, we get a huge amount of our power from hydroelectric. And so it can be great as long as it's done in a way to not impact the environment and the ecology. We have the issue with the salmon out here. There's other issues around the world. But if you can address those ecological issues with installing them, it can be a good source of power.
Geothermal.
There appears to be a lot of potential geothermal energy out there that, no pun intended, has so far mostly been untapped.
Energy storage.
Energy storage is critical for the renewables, and the prices have been falling very rapidly, which is great, but the energy density is just not increasing very much, and you're running into some physical limits. And so some of the creative ways of doing energy storage beyond just batteries is very exciting, and I think there's still a lot of work that needs to be done and challenges in order to scaling up the energy density and continuing to push the prices down.
Electric vehicles.
These are great. The challenge with any of the hydrocarbon fuels is that so much of the energy potential in them gets wasted as unused heat. Electric vehicles, even if batteries don't store as much energy, the electric motors are just so much more efficient at using the energy they do have. I have a 14-year-old car right now, and whenever I do replace it, it will almost certainly be with an electric vehicle.
Energy efficiency.
This is great. It can really help in so many ways of reducing the demand. The US, I believe, has been, I think, roughly flat in energy consumption on the scale of a decade or more, despite people growing because of partially increases in energy efficiency.
And then finally, fusion power.
I'm excited by a lot of the startups and the small work being done on fusion. I think for a long time, the international ITER effort sucked up all the available funding for fusion into that one project. And it's really great now to be seeing a lot of different approaches being tried.
Very good. Tom Nugent, PowerLight Technologies, thank you so much for your time.
Thank you. It's been my pleasure.
That was Tom Nugent, co-founder and CTO of PowerLight Technologies, a Seattle-based energy beaming company. I want to thank Tom for his time, as well as Martin Levy and Thomas Miller at Martin Levy Public Relations for setting this up. You can find plenty of pictures for this episode on energy-cast.com, as well as on Instagram and Parler at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loop. That wraps up episode 112. Be sure to join us next week when we discuss how smart meters are making our homes more energy independent. Until then, I'm Jay Downhauer. We'll see you next time.